Your computer won't turn on?
No indication on the home planet. It's most probable that the issue is with the power supply. We're observing absolutely no power being drawn. The power supply unit is not outputting any voltage. The auxiliary standby power source appears to be completely faulty. The main button and the toggle switch are both set to the on position, but absolutely nothing is happening. The computer simply will not start up. Alright then, let's get down to figuring out what the problem is. And the unit we're working on today is a Cooler Master power supply, rated at 700 watts.
This specific unit arrived as a generous donation. It was sent for repairs, but unfortunately something went wrong during the process, and the power supply is not working at all. As we can see, on the 12 volt line we're getting almost 700 watts, specifically 650 watts. Well, this is quite a good power supply unit, equipped with an active power factor corrector. There are more than enough cables here, all sorts of them, both 6+2 pin and 4+4 pin for the CPU. Therefore, it probably makes good sense to repair this particular unit. Let's open it up and see what exactly happened to it, what hidden pitfalls we'll find. Steve Michume ended up here with the from repair technician. And we're going to address all these identified shortcomings. Upon opening it up, we can clearly see that the power supply unit has been working quite extensively. The fan is certainly dusty, but it is still fully operational, so there is indeed rotation. There are no problems concerning this particular aspect here. The power supply unit looks quite a lot like a Corsair model. On the input side, we can clearly see the PFC system, an electrolytic capacitor, which we'll inspect, and we also notice a burnt PFC transistor. It's completely shorted out, this one. The voltage has been quite erratic here. We'll have to sort this out. On the output side, we have the DGS choke. That means we have 3.3. Here we have +5 and 12 volts and then -12. This is the standby power supply. There is also a rather strange transistor, Q20. I'm seeing a product like this for the very first time. I've truly never encountered anything quite like it before. Well, in that case, let's go ahead and figure out exactly what's going on here. I immediately desoldered all the wires and then I soldered in a 220 volt connector to make it much easier and more convenient to use this particular unit. Alright, so what's particularly interesting to highlight here? First and foremost, at the very input stage of this device, we have a dedicated microchip installed, and this particular chip actually integrates within itself several field effect transistors, specifically the SM03X MOSFETs. This initial microchip, the very first one, is primarily responsible for managing and controlling the APFC signals. Next, the PWM controller chip. It functions as a PWM controller, and also it is responsible for the PFC, the SM6800UX. Here, the backup power supply is here. At 662, is that what it is? I'm not entirely sure. Well, this is actually the very first time I've ever come across a chip like this one. Most likely what we're looking at here is simply a standard PWM controller, but the actual power switch, the main component, is located directly over here. It's this small power switch Q20. Well, this is absolutely wonderful. It's just fantastic. Right here at the output, we have a supervisor, and this is it. This particular one is our PS2H29. It's actually quite a decent supervisor. Most likely it will also be responsible for monitoring the current. It has comparators that are constantly checking the current's quality. Overload or perhaps no overcurrent condition. This means it also has an additional short circuit protection feature. Alright, first things first, we need to check the electrolyte to determine its current state. As for the APFC switches, well, that's all quite clear. It was soldered here and the transistor blew up. Most likely the entire CPFC circuit is completely faulty, so we'll just have to desolder it and then see what other issues we might encounter. We are measuring the electrolyte and passed, and its current condition is quite acceptable. Past 400 microfarads may pass. However, on the electrolyte itself, it is clearly specified past that it should be 470. Treat. No complaints about the electrolyte. Its capacity is, yes, a bit on the low side, but this won't significantly affect the power supply's operation. We also see soldering near the diode bridge. Right here we have a current shunt installed. This particular resistor was soldered for the APFC. Let's go ahead and check what the resistance of this shunt is. This is absolutely essential. It means it was either replaced or something else was done to it. As we can see, the shunt resistance is around 900 milliohms. Our power supply unit is most likely designed for 220 volts. This means that this particular unit will not be able to operate on a reduced voltage. Let's take a moment, by the way, to check the casing. It clearly states right here what voltage range the power supply unit functions with. Yes, I am correct. The power supply unit operates from 200 volts. This means that at a reduced voltage of 180, 160 volts, it's highly probable the power supply will enter protection mode because the APFC, which will draw a lot of current, will cause a significant voltage drop across this shunt. Consequently, the microcontroller will detect that an overcurrent will trip the APFC, and if there's undervoltage in the grid, the unit will eventually go into protection because the electrolytic capacitor won't be sufficiently charged. Consequently, the PWM switches will then transfer power. The voltage here will be reduced, so the output will no longer be 12 volts but lower, and then it's the supervisor's job. It will burn everything out and shut it all down completely. That's how simply it all works. We can safely desolder the power switch because it's faulty. There's nothing to do here. Since this inductor was desoldered, I'll desolder it too, so I don't have to remove the whole heatsink. Although I usually don't touch inductors, but since someone else repaired this unit before and desoldered the inductor, well, I'll do the same. Ej, to jest tylko...
It gives the impression that
the thermal pad was completely compressed and pushed right through. And as a result, this metal flange, its rear surface, came into direct contact with the radiator. Consequently, an electrical breakdown occurred precisely at the exact point of this contact. But this is just my current working hypothesis.
They over-tightened it, or the washer's wrong?
It's clear to see that the contact itself melted right here, meaning it shorted out, a very large current passed through.
By all appearances, well, there's a gasket failure.
This is the reason why we have this particular result.
But this is just an assumption.
You can clearly observe that the flange has ruptured and made contact with the main casing.
There is a resistor at about 5.1 ohms, but it's completely blown. It's totally shorted out and its resistance is incredibly high. I would venture to say, let's take a look at the kiloohm range. Well, yes, pause it's around, pause almost 100 coulombs. This indicates that it's precisely connected to the base, controlling the base of this transistor. The driver, yes, which supplies current to our MOSFET's gate, and consequently it's quite possible that the damage could have extended to the PWM output of the APFC. So the IC is definitely suspect. Although the second transistor, relative to its base, it appears to be completely intact. So I'll wash it now, clean up, and then continue to figure it out. I'm ready for the startup. I replaced the choke with a jumper, otherwise the electric current won't reach the electrolyte here. So instead of the choke there is a jumper.
I've set up a test point here to measure if there are pulses from the APFC, that is directly from the output PFC chip. It was more convenient for me to solder here than to the chip's pin. These are my leads for powering it. Well, we need to observe if the VCC voltage will rise here on the standby circuit, and this VCC is specifically what supplies power to our main power switches, the PWM, and also the APFC switches. So we will then proceed to check what the actual voltage is on the drivers themselves. But I've already managed to get it started thanks to this little helper board, and I've also discovered a rather interesting defect. So our power supply unit actually starts up.
The signals are now coming up, and we're ready to apply the main power.
Zetia, standby light comes on. I switch off the power. The standby light immediately goes out, even though there's still voltage on the capacitor. So this is the effect I'm seeing. The standby light turns on, then it turns off. So, using a smart power switch, I apply power, turn it off, apply power, turn it off. At first I was quite surprised, but then my attention was drawn to this particular circuit chain. So here's this rather interesting chain. The AC voltage from here is rectified through these two diodes, and then it passes through these dropping resistors. Yes, high resistance like mega ohm resistors. Here they are. Or maybe they're not mega ohm. What do we have here? 20, 0, 2. Well, 200, 200 plus 200, well, almost half a mega ohm. This sends a signal right here to the standby circuit to start the standby.
So, when there's no voltage present here, when we disconnect the 220 volts,
a signal comes from here, indicating that the standby unit isn't receiving signals from this point, meaning power isn't coming. Consequently, the standby unit enters green mode, which means it turns off and our electrolyte doesn't discharge. So the standby unit seems to be powered, but until signals arrive from here, it won't operate. The electrolyte will always be under voltage. Keep that in mind. If you reach in with your hands, it will give you a nasty shock. So our standby power supply is functioning. On the output of the auxiliary board, we see power is present.
Okay then, but that's not quite enough for us. Let's see how the power supply unit starts up.
We apply power, and we see the power supply has started. The power good signal is not lit. The PG signal, this very PG signal, is absent. Oh, there it is, and now it's gone. So, this indicates a defect. The unit is only partially functional, and the PFC isn't starting up. But the power good signal, ideally, when the power supply unit is operating in an idle state, the PG should appear. It showed up and then it vanished. We'll figure out why this is happening a little later on. It's possible it's because the PFC isn't coming up, but something tells me the problems aren't actually connected to the PFC. So what now? We're checking if signals are coming to the PFC, so we've already seen the PWM out. And here, everything is lighting up. The power supply is working, do you see? And the signal disappeared. And consequently, what we're going to do now is take a look at the oscilloscope. We'll then connect the probe.
So there'd be a magical good fellow, so let's turn it off.
Whoa! Be careful, there's high voltage present, right? And I need my subscribers alive, living people. But since they don't write comments, then dead ones are fine too. Alright, let's apply power and launch it. Here we see...
Alright, we're stopping now. PFC signals are definitely present. The frequency is around 120 kHz. Well, I'll be damned. I don't know, it should be that frequency. Usually I think it's around 100 kHz.
Well, it's quite possible that this is normal. So the amplitude is perfectly fine. That means 3 divisions, 15 volts. Everything is excellent. There are no complaints. So in principle, we are able to...
We need to restore the PFC circuit, solder the switching component, reinstall the choke, and then the unit will most likely operate normally. Many people leave comments. Those who simply like to resolve the components, yes. But you know, I don't have this specific type of PWM chip in my spare parts, and to just swap it out, that's not the issue here. Atsime et te conti et tetantis.
But we'd have to wait 3 weeks for it to arrive. I simply don't have that kind of time.
So we first check to see if the PWM controller is, well, at least somewhat functional, and now it's actually working perfectly.
And by the way, the golden key is still very much alive.
The key itself didn't fail because the flange just burned a little, but otherwise it's functional. If we open the supervisor's dense data sheet, we see the PGI signal. This is what we're most interested in, and here the voltage should be around 1.13 volts.
Right. So, this is the critical threshold value when the PGI signal must rise above.
That's why I'm talking about the PGI signal.
The power good input signal pin, meaning the incoming signal, which indicates that the power supply is coming up, this particular voltage needs to be higher than, well, basically 1.2 volts. It should be approximately 1.25 volts or even higher. Here's a rough schematic of how the PGI signal is generated. So this is our transformer from which a tap is taken and a standard diode is used.
Well, I'm not sure. I'm looking here at some resistor, right? It might be present or it might not be. And so there's a resistor here too, yes, which acts as a voltage divider with a capacitor for smoothing, and then it goes to the PGI input of the supervisor chip's first pin. But what I'm saying is that the voltage must be greater than 1.13 volts. Ideally, we're looking for 1.25 volts and higher. So we're going to connect to the chip's first PGI signal input right now. We'll check the chip's first pin to see what's coming to PGI and why our power good signal keeps appearing and then disappearing. What exactly is going on there? Let's take a moment to assess this situation. But the very first measurement with the oscilloscope, we're going to take it right here at this specific point. What I mean is we'll check if the voltage is rising up here and what its exact value is. Let's take a moment to properly assess this situation. Actually, no, let's not do it here, but rather after the diode. Okay, so specifically after the diode, we'll observe what the voltage level is at this point. Here it is, our main power transformer.
The output winding is located on this side. On this side we have the hot winding, yes, for the electrical connection, and on this side is the cold side of the transformer, the C cold winding.
Alright, from this side here, we can clearly see all of the tiny intricate details.
Alright, here they are, these tiny little components we're looking at. This is our diode, A6. It's essentially a 4148 type, and from here our neat little trace runs all the way to the supervisor chip, specifically to its very first pin. I've just scratched the surface a bit right here, and this is exactly where the signal comes in. Now, let's take a moment to check what the voltage reading is at this precise point.
Whether it's actually rising or not. Let's not forget, we are after all working with a power supply unit here. There is high voltage present in this particular section, you understand. And as you can see, 220 volts connects right here. And it could give you a really nasty electric shock.
So be careful, use it, and don't forget your safety. As always, my little helper board is my handy tool, which I use to control the power supply. So let's check the voltage we have after the diode.
Let's not forget that we're connecting everything. I'm connecting through a 60-watt lamp, an isolation transformer. Alright then, let's take a look and see what's happening here. Our standby voltage has come up, so let's go ahead and start the power supply unit.
We're going to start up the power supply and then we'll see that the voltage is indeed present. Let's make sure to record that. Alright, now the power supply can go ahead and switch off.
And we're going to take a look at what's happening here. We can clearly see that the voltage is quite high. Roughly, well, somewhere around 12, yeah, about 12 volts. Well, basically everything's okay. By the way, if you noticed, I don't think the power good came up just now. Let's check again. Oh, by the way, the power good signal isn't coming up at all right now. What I mean is, it completely stopped coming up. Before, it would start up for us, yes, and then it would just die out. But now it simply refuses to come up at all.
Let's now look at the signals we'll see at the input of the supervisor's first output. We run the block and we can already see a slightly different voltage here. Let's check what voltage we have. Da, what можем статистику și
So, here we can see the minimum, yes, the minimum reading is 1.16 volts. This indicates that our average voltage is, well, less than 1.2 volts.
So, this is precisely the threshold when the supervisor should, in theory, already understand, right? But it might not fully comprehend that the power supply is operating correctly, and therefore the power good signal isn't being sent to the motherboard. Consequently, our motherboard will not function. This could also be linked to our APFC not functioning, yes, but I'm not sure how significant an impact that would actually have. I mean, theoretically, I don't believe it should really affect things much. Alright, let's take a look. First, our power switch is functional and the choke is also good. Let's try to restore the hot side and power up the supply and see if power good stabilizes or not. There are power supply units that when the input signal is restored or when the APFC function is restored, the power good signal begins to assert itself. In this specific situation, I'm not entirely convinced that this will occur, but it's certainly within the realm of possibility. It might be configured in such a way that until there's no APFC, right, high voltage present, meaning anything above 330 volts, then accordingly the power good signal won't come up. Well, let's go ahead and verify this particular point. We'll conduct an experiment to confirm this.
So, we're going ahead and restoring the APFC section. I've already soldered in the ZV transistor, then I also soldered in the 5 ohm resistor, and after that I put the transistor back into its proper place. And of course, I've also returned the inductor to its original position. Otherwise, how exactly is the transistor supposed to function properly if there's no inductor present? Alright, I have successfully screwed in the transistor and I've also applied the thermal paste. In principle, when a PA is equal, we have the right to try to launch it. I immediately screwed in the second lamp because the APFC will be ramping up and drawing a significant amount of current. So let's go ahead and try to start it up. The startup is successful and our power supply unit turns off. And it's absolutely clear our supervisor is screwing us over. That supervisor is a parasite. I'm quite sure that's the problem. Yes, the power good signal isn't coming on at all. Take a look.
It just won't work. Alright, let's check what's at the output. The supervisor, it's acting up. No, the supervisor isn't to blame. Let's check the supervisor. FPO, that is the third pin. You see a high logic level. Now we'll start the block. The supervisor is functioning correctly and isn't blocking the power supply unit's operation. So I was making a fuss for absolutely no reason. Supervisor, I got myself all agitated. I have soldered two leads, the red one and this yellow one. The red one is VCC. We'll be monitoring VCC to see what's happening with it and why the chip's operation is being interrupted. Perhaps something is happening with the power supply? And what we have here are the PWM signals. No, actually, these are not PWM signals at all. These are actually our APFC signals. Let's observe how the PFC circuit behaves. Alright, so let's get Andre out. Andre, come on now, show us what you're capable of. Okay, we're going to supply the power now. Let's take a look. I've already set up the trigger. So, this is the situation that we have here. The red beam then is our VCC power supply, and the blue beam is our APFC in operation. So, as we can clearly see in this VCC, yes, there's a significant amount of interference present. So, this is our APFC. Alright, let's see how long this mess goes on. This mess lasts 1, 2, 3, 4, 5, 6, 7, 8, 9. Almost 200 milliseconds this whole thing takes. It's unclear to me. Let's take a look at the APFC pulse width. I get the impression that the incandescent bulb I'm using to start it should, in theory, flicker, meaning it should periodically draw current with some periodicity. And lately, yes, since the unit started turning off, I've noticed the lamp is always on. I mean, as if there's a short circuit, but here we see that pulses are arriving at the gate. Let's see what kind of pulses these are and how they look. This essentially probably gives the impression that the current sensor is faulty or something is wrong with it, some kind of unhealthy situation.
Alright, let's take a look at this whole thing in recording mode. Okay, exit. Yes.
And basically, that should be enough recording. Alright, let's see what we're looking at here. This is exactly what I noticed, the unhealthy situation. So, we have an attempted launch. There is an attempt to start, but the pulses are quite widely open. This means that we have the maximum current flowing through our MOSFET. By the way, here's our VCC power supply. Yes, there is noise, we can see the noise, here they are, these are the spikes. When APFC is working, noise is always present, there's no escaping it. So, essentially, the power supply is consistently present, that means there are no significant drops, it's approximately 14 volts. You see, the APFC signal is also quite normal. The amplitude is good, but it feels like there's no current feedback. Let's take another look at the lamp.
I was actually surprised thinking, maybe I just imagined it. No, when the unit started rebooting, I realized, okay, this situation isn't right at all. So I'll apply power now. The lamp is lit, it's not blinking, not even when viewed through the camera, and it's visually quite clear that it's not blinking. Although on camera, you probably won't be able to see it when it actually blinks, but then again, maybe you will, I'm not sure.
Not all videos, the phone might not be able to capture this, like an RLC meter, so the current sensor is located here.
It's located right here, and there it is, standing, this particular thick fat resistor. I believe I've already taken its measurement.
It's around 100 milliohms, right? Let's measure. Yeah, 90, well, basically 90 milliohms. Yeah, roughly speaking, 90 milliohms. Right, we need to check who is actually taking the signal from this stock sensor and how it's all set up. We'll look at the datasheet now. We'll check the datasheet. So from here, there should be a trace that measures the voltage drop right here on C, and all the information is sent to this combined controller, right? Let's study this information. Let's open our beloved datasheets.
Raise the shields of knowledge. This is where the information is, this is where the information hides. Alright, so let's take a look at our current sensor, where it's located. First of all, this is our iSense. Yes, this is it. Nyushka, yes, our very own Nyushka for current, the one that precisely takes measurements on our shunt. Our voltage, this is very important. Alright, let's move on. Let's take a look at the circuit diagram to see how it's organized, okay? First of all, this third pin right here is iSense. It clearly states PFC current sense on the diagram. In other words, this is the current sensing input, so that's what it is. The IL limit comparator is built precisely on it. So most likely that's where it all stems from. That's my assumption. There's nothing else to consider, really nothing more to add on that front. Oh wait, no, actually, it's not just a current that could potentially be causing us difficulties here. We might also very well be facing a significant problem concerning the feedback loop. This is the feedback right here. VRF, is that right? VRF, it really should be 7.5 volts. No, that's not quite it. Here it is. VFB. Here it is. We have an error with the feedback, you see. 3.5 volts should be present, should be on the divider, on the high voltage divider that is on the electrolyte.
Okay, so let's just quickly go over the main points here. When the main power switch wasn't properly soldered into its place, our PFC section was in fact completely non-operational, wasn't it? And despite that, the entire unit was still able to power on and function. It certainly didn't hold the load, you know, we weren't even applying a load to it, but there was no PG signal, no power OK signal, it was absent. So now when we start the power supply unit, it goes into an error, you see. After we soldered in the APFC power switch. Consequently,
all problems will most likely be specifically related to the APFC, and that means this electrolyte feedback is what's responsible for the APFC. So from here, you see these small high resistance resistors. Through these resistors, the voltage is measured, and this voltage measurement is then fed here. So this is the feedback indicating the voltage our electrolyte charges to, but it doesn't charge for us. The voltage doesn't manage to rise. It just barely twitches a little and immediately goes into an error state. What was that? And the second thing is the current feedback. Pause. So you see right here, the current flows through this particular shunt, doesn't it? Pause. Right. Pause, and then actually no, I mean on the contrary, right from this point here, you see this current flows and consequently the voltage drop across this resistor tells us exactly what current is flowing. And so the controller understands exactly when to stop supplying power to this very transistor so it doesn't burn out, right? Here, when you should, on the contrary, floor it. So in this case, we most likely have problems with the PFC. And that's obvious, meaning our shunt is intact. And we need to check VREF to what level the voltage rises through the feedback. So we can check these resistors, verify their integrity, and we will definitely do that with pleasure.
Don't forget to also check the diagram that's directly provided by the developer. So how it's all organized, all these various circuitries, the power supply voltages, everything is clearly shown on the schematic. Of course, manufacturers often deviate significantly from this diagram and can introduce many new things, but the core remains right here. The datasheet is truly the most important thing to know. So we have the third pin, here it is, the third pin, I've zoomed in a little bit. Our third pin, you see it right here, this is the iSense pin. It measures through a specific resistance what we're getting at this particular point, correct? So from this very spot, it takes its reference point from the negative terminal of the diode bridge. This is a reference point established through resistance. Here, I'm not sure, there's some additional circuitry in the form of 3 diodes, yes, and a capacitor. These can also go wrong or fail. This part. So besides this current sensor, yes, it's quite possible, yes, for this right? And then this is our what can directly affect our APFC, right? The module. And this is the most reasonable explanation, wouldn't you say? Because the transistor, our transistor has blown out. Consequently, it most likely took something else down with it as well. Perhaps the controller might have burned out somewhere, isn't it? However, if the PWM PTFC output is actually functioning correctly, yes, then in all likelihood, the controller itself has probably survived. And so what we have here, this is the control for the voltage level on the main electrolytic capacitor, which is specifically for the PFC circuit right here. VFB, that is, the 15th pin, is responsible for measuring what's happening on our power capacitor right here. So the voltage should rise to about 380 volts, approximately. Accordingly, my indicator will also light up if the voltage rises to 380 volts. Alright, and we can see here, this is a voltage divider with 2 megohms, and the lower arm of the divider, right? That's 26.7 kiloohms. Our specific values for all of these will be slightly different.
So I'm going to walk you through this entire circuit step by step right now. Here we have the positive terminal of the battery cell, and then right here we have a contact point. From there a 1 megohm resistor connects to another 1 megohm resistor, and our signal then arrives at the 8th pin of the SM03TX chip. Next, if this particular microchip activates, then contact number 8 will close with the very first pin, the electrical switching will then take place, and as a result, from the first pin, the signal then goes to the 15th output pin of the microchip itself. So we have a connection. Excellent. Next, here it is, our lower arm of the circuit, and right here we have a 1332 ohm resistor.
Here's the resistor.
I've checked the circuit continuity, so these resistors are not damaged. My main concern, really, is with the voltage, because it simply shouldn't be there.
I haven't measured it yet, but we can certainly do that too.
But I started tracing the current sensor signal path.
And what I actually found that was quite interesting, you see, so our current sensor is positioned right here, as you can observe. What I mean to say is this particular contact point here, it is precisely the negative terminal of the entire diode bridge assembly. So, we're starting our investigation right from this point, okay? However, my multimeter is currently defective, so we won't be able to see these 100 milliamps here. But that's not really necessary at the moment. What we truly need is a continuity check. So, using this contact, we're searching for the resistor. There it is, as shown in the schematic and the datasheet. We see that with this resistor, we have a switching connection, meaning from the negative side of the bridge, we come to this resistor. This resistor, well, it's quite small, isn't it? The datasheet doesn't specify its values. And that's really a pity. We can clearly see that 470 is marked 7 ohms. Now, let's proceed to check if it actually has continuity or not. Yes, it's not showing continuity because the resistance is quite high. Let's take a look and see what this resistance actually is. I have a special mode here. For kiloohms, well, this kind of multimeter. You all love using multimeters, don't you? Well, I also really enjoy using multimeters. Okay, we'll measure this resistor's resistance.
The resistor's resistance is very high.
So, what we have here is clearly more than 200 kiloohms. Most probably, the resistor, well, it's either desoldered itself, or it's simply worn out from constant operation, or perhaps it's just completely broken down. This specific resistor right here is 47 ohms, as you can clearly see, and visually speaking, it appears to be entirely intact. I have no complaints regarding it, but I managed to identify it specifically thanks to the datasheet. Yes, I mean, I don't have a schematic for this particular block. I'm only relying on the datasheet. Now, we're going to grab a different multimeter and we'll try to check for continuity using that one. Alright, let's go ahead and check it. I am measuring, and we see 0.57 mega ohms. Most likely, this is the resistance directly from this third terminal, and ground. And most likely, that's how it is, and we get it connected to ground. Yes, well, to ground. To the negative, most likely. So the resistor is probably just open, it's broken, right? But when a resistor breaks, one that's directly located near the input of the sensor, right? So, we have a comparator there. Ideally, it shouldn't have failed. The comparator has, I think, a comparator there. Well, most likely, it's a comparator. And the comparator has high input impedance. Therefore, it shouldn't have been damaged. So we pray to the electronic gods, desolder the resistor, and hope the combine survived, because I don't have another one, and waiting for one from China will take a month. Let's measure the resistance directly on our desoldered resistors. Oh, you see, it's 0.47, which means I was a little bit mistaken. The resistor does have some resistance after all. Alright, so what kind of resistance are you showing me here? He's got absolutely nothing. It's an open circuit. Well, it's showing some kind of megaohms there. Anyway, no, it's definitely an open circuit. It's not ringing out at all. It's open, dude. So what also bothers me is what's standing right next to it. I believe this ceramic capacitor. But judging by dim measurements, yes, it seems there's high resistance and ideally nothing else should have been damaged. Well, let's replace this resistance. Alright, so what do we have here? We finished up the soldering. Let's take a look now at the final result we've achieved. We'll apply the power and then we'll try to start it up.
And then the indicator lit up. Oh, APFC went right up. Haha! We have contact, we have contact. Yes. Oh, that's absolutely brilliant. What a fantastic job. Oh, just take a look at that. Oh, just take a look. What is it showing us there? What exactly is it showing us? There you go. APFC went up, it went up. APFC, why are you showing me some kind of nonsense? Let's go by the instruments. I agree. The instruments are our eyes.
Arabian Nights, a wondrous, wild and crazy plot, la 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 la, thrilling story full of magic, la 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 la.
Come on, let's get that little capacitor charged up right now.
Alright, just get it charged up already. Where's the power supply?
Oh wow, little air conditioner, get charged up quickly now. That's just excellent, it's absolutely wonderful. You've got to see this. I see it too. Super! So the power supply is working now. Power good is up, yes. So power good is finally working properly because the APFC started. By the way, we'll definitely check right now what's happening with power good and what voltage is present on it. I'm really curious about that too.
This is what's happening to him.
So the reason why when there was no APFC we had an undervoltage and consequently power good wasn't appearing, but now our APFC has come up. Let's check what the voltage is there because it was right on the border, you know, between working and not working. To cut a long story short, look, and also if you, well, notice, yeah, if you pay attention to such small details there. By the way, those who want to order the little helper board, you know who to contact. If you really pay attention to the nuances, these little details, right? Look, when our shunt resistance is quite significantly high, like 100 milliohms, that's an incredibly large amount, you see. Then we notice that although the lamps do flash, the capacitor charges up quite rapidly, and the total number of flashes is very, very small. So, when we're dealing with a really tiny shunt, something like 20 milliamps, you know, in that approximate range of 20 milliamps, that's when a lot more current gets pulled from the wall socket. But how much more exactly? So, it's, how should I put it, aggressive. And the light bulb, as if, glows even brighter and for a much longer time, right? This happens because there's an overcurrent situation. The bulb creates a huge amount of resistance and consequently, the APFC doesn't receive sufficient current, causing it to constantly try to reset and then struggle. So, look, I'm pressing this button now, and you'll see how quite quickly the electrolyte gets charged. It's not because the electrolyte is bad, but rather because, well, first off, the electrolyte there is, of course, 400 microfarads. Yes, 420. It's a fairly small micro... Well, how small? It's normal.
Here, take a look at this.
Well, the light didn't even flicker practically. I just started it up.
Look how fast they are, huh? And that's it. And the block starter.
So, you don't get that effect when I press the button on the more powerful units, yes, but of course those have larger capacitors, yes, significantly larger, it goes without saying. Well, these kinds of small minor details you really have to pay attention to.
Again, dear friends, this is amateur content, okay? There's no real accuracy here, okay? There might be errors or some wrong ideas expressed, so keep in mind, these are all my thoughts, okay? This doesn't mean that you should repeat or do exactly the same, okay? Those are simply my current findings and methods at this point, at this particular stage of my life. Yes, this is precisely how I'm dealing with the issue, right? Some professionals, they just look at it and visually they can tell, all right, this resistor needs to go, this capacitor has to be replaced. They just have a feel for it. I haven't learned that yet. I'm still a bit foolish. I haven't quite reached those heights, so I'm just showing you how I manage to do things.
And now we're going to check the power good signal, right? Okay, pause. Well, not exactly power good, but PGI, no pause. So we'll connect to the first output pin and then we'll power up the entire unit. You can clearly observe that the voltage has significantly increased, consequently our entire system is now fully operational and the power OK indicator is steadily rising. The overall system voltage reading is now approximately practically 1.5 volts. So this is a clear value, exceeding I think 1.25 I believe is the threshold, right? But here it's almost 1.5 volts. So this is a clear indication that APFC has started.